In Lesson 3, we'll be dealing with the subjects of waveforms, measurements, and power. And if you break it down, in the waveforms area, we're going to be studying both averages and RMS. Averages and RMS for the following 6 kinds of waveforms. We'll do average and RMS for constant waveforms, for sinusoids, for uniform pulse trains, for triangular waveforms, for rectified sinusoids, half wave rectified, and for rectified sinusoids, full wave rectified. So for each of these 6 situations, we'll study average, RMS. Now when we're finished with doing that, we'll try to tie this all together by doing a study of Fourier series and spectra, energy spectra, power spectra, voltage spectra. So we'll be dealing with power spectra, or spectrum, plural being spectra, and so forth. So that will be the first 1/3 of this lesson. Then we're going to do the next 1/3, which will be in measurements. We'll deal with instrumentation. Then we'll deal with power. That'll come later. So let's get started now on the first 1/3 of this on waveforms. Part 1, averages of these 6 waveforms. Well, we'll get started with averages of various waveforms. I'd also like to mention the fact that we will be dealing with periodic waveforms for this entire lesson. We'll be talking about every waveform, every pulse train, everything we think about will be sinusoidal, or not necessarily sinusoidal, but it'll be periodic. Now, what happens when things are not periodic? What do you do? Well, that's a subject for a different lesson. And just to put things in perspective for you, when you're dealing with periodic signals, as we will be in this lesson, the Fourier series becomes a very powerful tool to use in that situation. However, when you go to talk about a non-periodic signal, then we go to the Fourier transform. So the Fourier transform is the powerhouse tool for non-periodic signals, whereas the Fourier series is used for periodic. So, without repeating myself, this will all be periodic signals for the rest of this lesson. We want to find an average value of a waveform, and this one's a little bit unusual. It looks like this. Let's make it be a voltage as a function of time, and let that voltage take on a constant value. Our first example, we have a constant voltage, and this voltage goes on to, let's say, some time t, and it stops at that point. And let's say this is all we had to study. There's time 0. We ask ourselves, well, what's the average value of this waveform? Well, I think it's fairly simple. Without doing any kind of mathematics, the answer is whatever this value is. Let's call this value V. It goes up to V volts. Then that's the average value. Now, technically, what we're doing is this. We're finding the area under this curve over a period. Now that's going to be repeated many, many times. We'll be finding the area under a curve over a period and taking that net area and dividing it by the period in order to get the average value. So it becomes almost trivial for a constant function when we start talking about what's its average value. So let's say a constant function has some sort of an arbitrary period, and if we use V volts for our example, and if the period is chosen to be whatever you want it to be, then it's obvious to do any kind of mathematics that the average value is equal to V volts. That one is easy, that one's straightforward, and now I'm ready to go on to talk about the sinusoid. In the case of a sine wave, as we have in this example, again, no math is needed to show that the average value over a period is equal to 0, because the area under the curve, the net area over one complete period, is exactly 0. Mathematically, what happens is that the DC meter actually calculates the integral over a period of this waveform and records that number and displays that number, And that's what the answer would be to what is a DC value of a pure sine wave. Answer is 0.